try to do as much as we can of GLQ number 14 right now. Okay. And we'll do at least probably about 20, 30 minutes next class, depending on how we get through this. Alright? So, distinguish what a conservative force is, and give an example of each, then give this path analogy business. Alright, so then I talked about this before the quiz. A conservative force is a force that can be reversed, okay, or that doesn't change the mechanical energy of the system of a system. So, for example, if I'm pushing this ball, yes, the object is gaining kinetic energy. Well, that means I'm losing potential. Does that make sense? So that force is not changing the total mechanical energy of the system in question, right? Now, when you talk about friction, when friction slows something down, that energy of motion that used to be in the object is not going to potential or to kinetic, right? So it's not like it's gaining, the floor gains kinetic energy, or that the floor gains potential energy, right? The kinetic energy is just not transformed to potential, right? When I push the ball, the potential that's in my arms muscles is becoming kinetic in the ball, right? So it's a transfer between potential and mechanical and kinetic. So it's still mechanical energy. That means it's a conservative force, right? So when I pick up a ball and raise it up, right, I am doing potential energy force, right, to give it potential, right? So potential to potential. Does that make sense? So I'm not changing mechanical energy. So that's a conservative force. Now, when sound gets produced, a seismic wave gets produced, or these disorganized entropic forces act, you can't capture that energy back and put it back into potential, back into kinetic. Does that make sense? Yes? Okay, so that's what it is. Now, this path analogy business is this idea here. It's very important, okay? This is how you tell. This is a test. You know how we were talking earlier today about, I just mentioned earlier today, when you have that, when you were wondering what should the best course of action be, the test should be, is it the most loving action that you could take, right? There's a test for this too. And this is a test, okay? You think of a path. So if I pick up a path like from going from here to here to here to here. If you're talking about a conservative force, all right, it doesn't really matter what path you take. All that matters is the displacement. Are you with me? So think about it in terms of gravitational potential. If I do this, then this, then this, then this, then this, and this, and this, and this, and this, at the end of the day, I gave it this much potential. So I start from here. You know, I did all that, and ended up here. That is exactly the same thing as grabbing it from here and putting it here. Are you with me? In terms of how much gravitational potential was added. Does that make sense? Now, if friction, you're talking about friction, doesn't matter if I did all of that or versus that, in which case there was more air resistance. Are you with me? So the path matters for the amount of energy gained or lost when you're talking about a non-conservative force. Are you with me? But it doesn't matter when you're talking about a conservative force. Does that make sense? Okay. Before we actually talk about this mechanical energy thing and how it relates to Newton's first law, let's talk about the actual formulas that govern this chapter that were in the quiz. So we have kinetic energy is mv squared over 2. So what matters to know how much energy something has? Kinetic energy something has. What matters? The velocity and what matters more? In a way, velocity, because it gets squared. So let's think about it this way. There's a mosquito going at 300 miles an hour and a car going at 300 miles an hour. Now it's the same velocity. What matters is the mass. Now, that's why it doesn't matter if you get hit by a really fast-moving mosquito. It's not going to hurt you. A really fast-moving penny falling from the Empire State Building is not going to hurt you because it doesn't have enough. So it doesn't have enough kinetic energy, even at that velocity. Right? But if you accelerate it really fast, it could hurt you. Are you with me? So you can make up for the lack of mass. Right? Now remember, this is meters per second, but that's in kilograms. So if something is like 1,000 kilograms, it will make a difference by the order of 3 magnitudes. So it could make a difference. Does that make sense to you? Inside, guys. Inside. Oh, you got it from there?
Yeah, I got it.
Okay, don't get it from there anymore. From the inside. All right? Does that make sense to you guys? Now, let's also talk about this. Velocity business. How fast is this ball moving? Right now. How fast is it moving? Right now. Okay, so how much kinetic energy does it have? It depends on your frame of reference. Very good. Get Legos, yes. Okay. All right, well, it's going to be okay. All right. So, don't go all Hulk on us. Now, if you are sitting in a space shuttle, right, and you're seeing the Earth move, you realize this ball has a lot of kinetic energy. In fact, we're close to the equator here. Let's say we were in the equator. It would be doing 48,000 kilometers of circumference in 24 hours. So that is really, really fast. This is like going at thousands of meters per second. Are you with me? So this is going at spaceship speed. It has a shitload of kinetic energy. Does that make sense? Then remember that this thing goes around the sun in 1 year. So even if you stop the Earth's rotation, this thing is going around the sun. That's a huge circle. It takes 8 light minutes for light to get here, and that's the radius. So if you do 2 pi r with that, and then you figure out how the distance is, and you divide it by 365 days, and then you divide it by 3,600 seconds, and then you divide it by 24 hours, so you can get the actual speed of this ball going around. It is incredibly fast. We're going at something ridiculous. Humans have never made something go that fast. Are you with me what I'm trying to say? And then if you think about, actually a human spaceship could not do Earth's orbit in the same time Earth does Earth's orbit. You follow what I'm trying to say? Unless we put it on Earth's orbit. And then it will do that. Right? And it took us, just to give perspective, 50 years to get to the edge of the solar system with the fastest ship ever, right? So it's not depends on the, so what, that means something though. What I'm trying to get to is kinetic energy is meaningless. Absolute kinetic energy is meaningless. Why is it meaningless? Because it depends on what? On the observer. Are you with me? So if I say how much kinetic energy does it have, that is a meaningless question without the observer. Does that make sense? Potential energy is the same way. Potential energy is mgh. But what part of this is relative? The height. So how much potential does that have? It depends. It could fall to the ground if I take the table out. And if I take the floor out, it could fall to the center of the Earth. And then it could still fall to the center of the sun. And it could still fall to the center of the galaxy and so forth. So the amount of potential that you have is also depends. By the way, to have potential, you need to have at least 2 things. If this was just an object, that's it. How much potential would it have? If it's just an object, you can't have potential because you need another object to set the ground. Are you with me what I'm trying to say? Does that make sense? So potential energy only makes sense in the first place once you have at least 2 things. So potential energy requires a system. Does that make sense? Right? Can you have kinetic energy without a system? Sure. But even then, it's meaningless without a reference point. Which is why in science, it makes more sense to talk about this. Change in kinetic energy. mv minus v1, these are squared divided by 2. That has more meaning. Okay? Also, change in potential energy, or mg, h final minus h initial. That has more meaning. I'll give you an example. Check this out. If I put an object at 0 and raise it to 20, all right, I'm adding mg times 20 potential to this object. Does that make sense? But if I call the 0 down here, and I call this 20 and that 40, and I raise it from here to here, are you with me? So I was at mg20 and I go to mg40. I'm still adding mg20 potential. Are you with me? So it doesn't matter where I put my 0. The change in potential is always the same. Do you see that? Are you with me? That's why change in potential has more meaning than actual potential. Does that make sense? and when we're talking about things. Okay. Now, mechanical, by the way, there's another type of potential energy that's of a spring is 1/2 kx squared. All right, that's the potential of a spring. This is gravitational potential right here. The last one I want to talk, so let's do the next question and then we'll stop there. State the conditions necessary for maintaining mechanical, this is a conservation of energy thing. All right, and relate this to Newton's first law. What is Newton's first law about? Inertia. What does it say? That's like I want the one that you summarize everything in one statement. You can't change the momentum of a system unless a force applied to it, right? Or you could say you cannot change the energy of a system unless a force applied to it. Or in other words, you can't change an object's motion pattern unless a force applied to it. So the idea here is you can't change the energy of, see Newton's first law, rephrased in energetics terms. You can't change the energy of a system unless a force, an external force, acts on it. So unless you do work on the object, its energy can't change. Does that make sense? That is what that is. So what is mechanical energy? First of all, you should write this in the question. Mechanical energy is what? Potential plus kinetic. And according to the rule, that number is supposed to stay the same, this M. You can trade between the two. Are you with me? So you can go, whatever you gain in kinetic, you lose in potential. That's another formula that we need. All right? Whatever you gain in kinetic, you lose in potential. Or if you lose kinetic, you gain in potential. They're the opposite. Are you with me? But that's only true so long as no work is done. No external force acts on the system. The moment a force acts on it, all bets are off, the mechanical energy can change. Does that make sense? Okay. So there's another formula you can think about. This is very important. If you do work, you can gain potential. Or if you do work, you can gain kinetic energy. All right? And work, remember, is a dot product between the force and the distance for which it acts to, or F, D, cosine of theta. Make sure you have these formulas because I'm not going to write them on the board next time again. One of you guys could actually, when you come in, write them all down so we can start with the formulas on the board because we're going to need them for the rest of the questions. All right? But I want to point out something important here. This is very important. We'll finish here. When I raise this up, I'm doing work, right? Okay? Now let's talk about falling. What is this falling? Did it gain kinetic energy? Why? As it falls, does it gain kinetic energy? Why? Because it's losing potential. That's one way of thinking about it. You can also think of it as gravity is doing work, so it's gaining kinetic energy. Does that make sense? But careful. This is very important. Don't think of it at both ways at the same time. Either you look at this with that formula, lost potential, therefore gain kinetic, or you think of this with that formula. Gravity did work, and therefore it gained kinetic energy. Are you with me, I'm saying? Either way, the math is the same, though, because what is work? Force times distance. And what is the force that's making it fall? What is that? Weight. Weight is mg, and it falls over a distance of that height, h. That's the same thing. Are you with me? We'll talk more about this next time. I'll see you guys then. Also, come with a plan for mastery because you will do have the class of mastery. See you guys next time.